be, let me introduce our keynote speaker. So Ian, you can share your screen and share your video if you're okay with sharing.
Yeah, it says, good morning. It says I can't start my video because the host has stopped it.
Okay. So
you better...
that is why we have some buffer time here. Let me fix that and then introduce you. Ian, all right, should be fine now.
Okay, let's try again.
Yeah. All right.
And you can probably see my slides as well.
Yes, we can hear you, and you should be able to share your video as well.
Yep.
All right, you're coming up. All right. So it's my great pleasure to have Ian Foster, who's our keynote speaker. So he is the Arthur Holly Compton Distinguished Service Professor of Computer Science at University of Chicago. But he's also Senior Scientist and Distinguished Fellow and Director of Data Science and Learning at Oregon National Lab. So he has a BSc degree from the University of Canterbury in New Zealand and a PhD from Imperial College in the UK, both in computer science. Okay. His research is in distributed, parallel, and data-intensive computing and their application to scientific problems. He is very distinguished. He's a fellow of the AAAS, ACM, BCS, and IEEE, and he has received the BCS Loveless Medal, the IEEE Babbage, Good, and Kanai Awards, and the ACM IEEE Ken Kennedy Award. So he's also director of the Trillion Parameter Consortium, which is leading some of the community efforts in creating foundation models. So with that, I will very happy to hand over the reins to you, Ian. So thank you for being with us, and we're all super excited for your talk.
Hey, good morning, everyone, or good afternoon for some of you, perhaps. It's a great pleasure to be here. It's such a wonderful program that Venkat has put together, and I'd love to be attending all the lectures and participating in the hackathons. I won't be able to do all of them, but I'll try and do some of them. So I'm asked to provide an introduction to foundation models for science, which, of course, some of you are expert in, and some of you are less familiar with. So I'll try and cover a bit of detail and a bit of high-level stuff as well, and everyone should feel free to ask questions. I don't think I'll see questions on Zoom, so you may want to just speak up and ask if you have things you want to say.
Yes, I'll be moderating the Q&A. Yeah.
Good, excellent. So just a few words about myself. So as said, I'm at Oregon National Lab, which is, if you're not familiar with the place, it's about 25 miles outside Chicago. It's where Fermi moved his nuclear reactor after the war, once he got it going in the squash courts at the University of Chicago. It's quite a lovely green site, but the parts that I'm most interested in actually the Argonne Leadership Computing Facility, which currently runs one of the world's fastest supercomputers, which is relevant to what we're talking about here. It's also home to a place called the Advanced Photon Source, about 5 microseconds away, which is not that relevant, except that it's a source of big data that motivates our interest in foundation models, among other things. So, why are we interested in foundations for models for science at the moment? Well, one reason I would suggest is because we live in such interesting times. So on the right here, actually, we show it's a picture from a light source showing light source brilliance, the number of photons generated per second, basically. It's the actual measure is the density of photons, but times the number of photons. But increasing far faster than exponentially, and certainly far faster than Moore's law, which, as we know, is itself arguably starting to trail off. And so, yeah, this is a general situation for science, I would say. Data volumes are growing much faster than computing power. Problem complexities are growing rapidly, I would argue, for the simple reason that scientists have solved many of the simple problems, so we're just left with the hard problems. Of course, the number of researchers is not growing particularly fast. So if we want to solve the grand challenges of our generation, whether they are clean energy, plentiful clean water, climate change, or the other problems that may concern us, we're going to need to work differently. And of course, we do have some things we can call upon, very powerful computers and new computational methods. But in general, we face challenging situations. And if I could refer back to some historical literature. Oh, no, actually, first of all, I'd be interested to know what people will think of this argument. So, our problem complexities are increasing exponentially. So if we keep applying the same methods we've always applied, we're going to be solving exponentially fewer problems or doing exponentially worse. If we keep improving our capabilities exponentially, then we're going to at least stay on at a constant rate. If we want to do better, we need to actually improve what we're doing super exponentially. So this is sort of, I think, a challenge we should all be thinking about. And I would say, is a motivation for this current workshop. Business as usual is no longer satisfactory. And someone else wrote about this, Lewis Carroll in the Red Queen's race, talking about, if you, as Alice said, if we run very fast for a long time, we'll probably get somewhere. And the Queen says, well, that's just going to keep you in the same place. If you want to get somewhere else, you've got to run at least twice as fast as that. Okay, so that's why we might be interested in AI methods. So some of you have probably seen a picture like this before, talking about the evolution of the modes of science. Of course, empirical science, simply observing things, theoretical science, coming up with predictive laws that can then be validated. It's now before most of ours, we were born, but not that long past, computational science emerged as a third paradigm for discovery. And, as exemplified here by a picture of Jim Gray, a famous data scientist, data-driven discovery was recognized in the 2000s as a fourth paradigm of discovery, not as a replacement for the others, but as a potential complement to the other methods. So some people are now arguing that we need and are starting to develop a new form of scientific method based on applying all of the previous methods in an accelerated mode in which AI methods are used to, for example, generate hypotheses, test hypotheses, synthesize across scientific knowledge in ways that individual humans are not able to do without the aid of these methods. And I think you'll probably mostly recognize the loop on the right. This is at least a representation of the scientific method as widely applied. And here I expand upon some of the steps involved in that scientific method and highlight in red some of the ways in which AI, and particularly foundation models, may be used to accelerate different elements of this process. So if we were to start at the upper left here, taking large bodies of scientific knowledge, for example, the scientific literature, and extracting, integrating and reasoning about that knowledge. That's something that we're able to do using foundation models, as we'll see later today. Based on that, we may be able to generate new hypotheses. You'll hear about that from some speakers. With a hypothesis and perhaps a proposed method for testing our hypothesis, we may then want to program an automated robotic lab to actually perform an experiment, or perhaps arguably, alternatively, we might want to program a set of computational tests to perform to validate a hypothesis, and so on and so forth. I won't go around the entire loop, but the point is that AI methods can be used in all of these processes. And so, of course, being able to call upon AI methods to solve problems is all very well, but only if they are likely to be effective. And there is of course, considerable evidence that so-called artificial intelligence methods have rapidly increasing capabilities in many fields. So this is a fairly recent report that looks at a whole set of different benchmark tests and looks at their the capabilities achieved by AI methods over time, as reported in the best available results, and normalizes them to human performance as reported in other publications. So these are somewhat approximate measures, but nevertheless, it is impressive to see how quickly various measures of human performance, AI methods have improved in capability, and in some cases, in things like handwriting recognition, language understanding, image recognition, are performing better than ordinary humans, not necessarily human experts, but ordinary humans. In other areas like code generation, complex reasoning, math problem solving, these AI methods are improving rapidly in performance, but have not yet reached human capabilities. So that's pretty impressive. And you can see perhaps some leveling off at the top of some of these, but that's only perhaps because they're reaching 100% by these measures. It's not necessarily showing that the methods are failing to and continue to improve. So that's a bit of background. Now, I thought we're going to be talking today about foundation models, and the foundation model is, in a sense, a supercharged multimodal version of a large language model. So I want to spend a few minutes talking about large language models, the likes of ChatGPT and so forth, just to level set us in terms of terminology. So what is a large language model? And I'll first of all present an incredibly simplistic perspective and then drill down a little bit on some of the details. So, this is one view of a large language model. It's basically a black box that you can ask it. You can present it with a word or a sequence of words that will keep giving you the most likely next word in a sequence based on its knowledge of the ensemble of human discourse, or whatever ensemble of human discourse it's been provided with, as encoded in the language model parameters. So you might recognize, if you're very astute, that this is the first few words of a dialogue in the Alice in Wonderland, which we may see on the next slide. Yeah, here it is. Alice, would you tell me, please, which way I ought to go from here, etc., etc. So a large language model trained on the ensemble of English language might be able to generate dialogues like this, probably not the same for various reasons, which we won't go into, but similar. So how is the large language model trained in the first place? Well, there's a large corpus of text. This could be huge quantities of web data, books, papers, other documents, each of which contains many sentences. The large language model training process then simply is concerned with setting values for parameters in a very large, deep, multi-layer, deep neural network such that when a word is presented as input to the network, you'll get something sensible out the other end. And the way that this training is done, in one typical instance at least, is to present a series of masked sentences in which the last word is omitted. So here are 5 taken from the first sentence of the text on the left. And then the parameter values are updated, modified via a training process such that you're likely to get the next word in the sentence that's provided. So starting point for a large language model, you're simply training a neural network to be able to predict the next word in a sentence. Sounds almost trivial. What is wonderful, of course, is how we can go from there to far more powerful capabilities. So let's first of all look at what's involved in this training process. So as I think Venkat mentioned, this is a very compute-intensive, labor-intensive process. A typical model, for example, the GPT series of models involve neural networks with billions of parameters. We're getting up to hundreds of billions in some cases. We won't go into the detail of how those parameters are organized, but they're basically lots of highly connected neural network components that are linked together in various ways. We then have trillions of tokens. A token is basically a measure of training data for text. That might be basically, you can think of it as a syllable in many cases. And then we are going through this process of training by repeatedly updating the parameters until it's able to effectively predict the next token. So there are three interesting aspects of this LLM training process, which really make it different from some prior approaches to AI. So first of all, it's entirely self-supervised. What that means is that no human has to go in and label the data that we're using for training. We're simply creating the training data by masking words, and then, of course, evaluating whether the model can predict the next word accurately. We perform this pre-training process, which to determine the parameters. So the parameters aren't determined by any other process beyond that. And thirdly, it's auto-regressive in the sense that we keep presenting the model with sequences of tokens so that the prediction made for the fifth token will depend on the predictions made for the fourth, third, second, first, etc. Tokens. So those are terms that you'll come up with as we go forward. Anyway, so that's the training process, and that produces a trained model that is typically very good at predicting the next token. So is that useful? Well, sometimes you might use that directly. More often, at least historically, what one would do is then perform a fine-tuning process in which we further update the parameter values of the model based on not, in this case, self-supervised, but via supervised learning process. For example, say we wanted to come up with a model that would, given a sequence of text like this shown here on the bottom left, would be able to predict the topic of that text fragment. So that could be useful for various reasons. We would fine-tune our model by, in a fairly rapid process, running pairs of this sort through the trained model, the pre-trained model, and updating the parameter values until we got consistent predictions that matched with the label. So earlier on, I think someone was mentioned that a large language model, once pre-trained, can then be adapted quickly to many different purposes. One way of adapting is by doing this fine-tuning process. And as I think I show here, the fine-tuning process, the tuning process might involve thousands of GPUs, or more often nowadays, tens of thousands of GPUs running for months. The fine-tuning process might be, a handful of GPUs used for just a few days or less. And so given a single pre-trained model, one may produce many fine-tuned models for many different purposes. Now, there are other aspects to training which relate to a process that's referred to sometimes as reinforcement learning by human feedback. And that is, one purpose of that is often to further adjust the model outputs so that they are consistent with whatever modes of use one might want to see. So you might want to prevent the model from saying things that are rude, racist, sexist, etc. And that would be a process of that aspect is handled by the reinforcement learning by human feedback component. But I won't say more about that today. Okay. So far I've been talking about large language models. Now let's go in and drill down on foundation models, which, well, one rather cynical view of foundation models is to say that it's what people on the west coast of the US call large language models. The term originated in a report from Stanford, but it's more generally, the term is commonly used to mean multimodal models, models that don't just deal with text. And of course, in science, other modalities, whether it's figures, videos, scientific data, are of high importance in terms of our AI model capabilities. But this is a picture from the Stanford paper I just mentioned, and it has some interesting things to say about how AI has been evolving over the last 20 years or more. Back in the day, before most of us were born, AI was things like expert systems, hand-coded rules that would tell a system what to do under various situations. Machine learning, was a major advance. There, the idea was, instead of telling the program what to do, you would use various methods to infer from a set of supplied, typically labeled data, what the computer should do in some particular instance. So that there's all sorts of machine learning methods, as I'm sure many of you know, that are still very effective in many even scientific cases. And then deep learning emerged, and one way of thinking about the difference between deep learning and machine learning is, in machine learning, typically the user, the scientist, has to hard code the features that are going to be learned on. With deep learning, the features emerge automatically. And then foundation models, which are basically very large deep learning models with some other interesting features. Even as I say here, even advanced functionality emerge, and I'll explain what in-context learning is in a moment. So that's one difference. Foundation models capabilities emerge, and then there's this other fascinating notion of homogenization. Machine learning, in principle, allows different learning algorithms to be the details of the machine learning algorithm to emerge from the learning process. With deep learning, the architecture emerges, and with foundation models, as we'll show, we can use the same model architecture. For example, GPT-3, GPT-4, other modeled architectures that we'll talk about, for a wide range of different problems. During the training process itself, the parameter values are being set in a way that will address the needs of a particular class of applications. So it's pretty miraculous.
So Ian,
okay.
just to be a little more interactive. So can you speak a bit more about homogenization? There are different definitions, and
I'll say a few words, and if
you
you might have other things you'd like to add as well. There was there's a tremendous literature of people fiddling with the architecture of neural networks to try and optimize them for particular purposes. Arguably, and so people would write a paper saying, well, for this particular class of problems, this network architecture performs better than this other network architecture, and the network architectures might vary in terms of the types of nodes in the network, their connectivity, the number of layers, and so forth. with the GPT-3 and 4 and Llama, the various Llama models and many others, there's a single big model that is trained. It has a particular architecture, which is, of course, significant, but you don't use a different GPT model architecture for property prediction in material science versus some other application in material science. The parameters in the model seem to be end up being set during training in a way that can deal with different applications. How would you say? Would you like to add to that?
I think you covered it. I'm just like, some criticism or, people who doubt some of these models say the first class you described, the non-homogenized, the specific models are narrow and deep, whereas foundation models are broad and shallow, right? So there is that angle as well. So, but I think the definitions are fine, but when you lose specificity, some people argue that you lose utility. But I see that as a preconditioner or as an assistant to get you to where you want, right?
Yeah. So one concern that people will express, and quite rightly so, is we don't really have a very good theoretical understanding of why these models work and how they work in different settings. So it's the arguments that are made for homogenization and effectiveness are typically based on experience, and rather than any theoretical arguments. And that means, well, a couple of things. One is it's easy to be fooled by maybe someone has just got better data, training data, or better, a bigger computer, and therefore their method works better. It would be nice if there was a more theoretical understanding.
Yeah.
Okay, so let's so that's what a foundation model was. Let's say a large model trained on large data sets from many sources. There typically will be, some additional training to improve the human interaction experience, to prepare it to be able to engage in conversation, to prevent it from saying inappropriate things. Fascinatingly, it often exhibits this emergent behavior, as we've mentioned, and it's trained by a process that is incredibly expensive. The model itself is very large as well. Those are two different things. Very large, trained on lots of data, requiring large amounts of time, and then can be used for a wide variety of different purposes. So let's move on, and I wanted to say a few words about this one particular emergent property, which is an interesting one. And this is what's sometimes called in-context learning. So the GPT-2 and earlier models, the typical way of applying them was, as I just said, you did pre-training and then you did fine-tuning for a particular purpose. Now, so later models, which differ primarily in being larger and trained on more data, not other things as far as we know. They have this interesting property that they can be adapted for some downstream tasks simply by providing a prompt describing the task to be performed, and then they seem to, the property of being able to solve that task then emerges from the model itself. So let's give you an example. So here's a, say we want to use a LLM for property prediction. This is the prompt. So you can read it. Some of you are expert chemists and some of you are not, but the idea is, given a particular representation of a molecule, we want to be able to predict whether or not the molecule will penetrate the blood-brain barrier. So we could simply pose that question and supply a smiles, and then ask it to predict whether or not it penetrates the blood-brain barrier. So it turns out it says no, at least when I tried it yesterday. This is GPT-4o, I believe, which is not correct. Okay, so it gets this wrong. But now let's look at the in-context learning context. So here the prompt is the same, but now we give a set of examples. This ICL stands for in-context learning, a set of examples, and then ask the same question, and this time we get the right answer. So obviously the fact that we get the right answer in the first case and not in the second, when you've got a 50% chance of being right or wrong, is not very revealing. But people, of course, have done much more exhaustive studies of these sorts of things, as noted, for example, in this paper reference at the bottom left, and find that you can teach a large language model a great deal simply by providing it examples in this way, which in a sense is an emergent property. This was not expected when people trained GPT-3 and GPT-4, but it turns out that it's able to do this. And here's some people have studied this in some detail, looking at how well I can't remember which model this is actually, but anyway, doesn't matter too much. This is this is the number of examples provided in context. So no examples, zero shot. That was what I showed before, and accuracy is only 10%. If you go up to one example, then the accuracy for the larger model increases, and it continues to increase with more examples up to 10 or 20 examples here. And interestingly, as you can see, this ability to do multi-shot learning is not really present with this 1.3 billion parameter model, is somewhat with a 13 billion, and becomes quite substantial for the 175 billion parameter. So that's an interesting observation about the power of multi-parameter foundation models. So let's look more generally at how we improve foundation model performance. So this is a simple little cartoon of, again, this is the pre-training process of a foundation model. Lots of materials being provided as input. You're running things through computing loss, updating the parameters, and then once you've got the parameter values, we're running the same input through to find out what the output token would be given a particular set of inputs. And training is the expensive part, inference is the cheap part. So what makes these things perform better? Well, basically more parameters, more training data, more training compute. And on the right-hand side, we'll get into this later, more context. For example, the in-context learning example I gave you is providing more context. And also richer workflows, which we'll really get to in later talks. But the idea that you don't simply use a model as a one-shot, ask a question, get an answer, but you may be applying a sequence of questions and improving performance in that way. So this fact that model performance improves so rapidly, as we just saw here, with model size, is an interesting phenomenon, because it suggests, we have a couple of different things we can do if we're trying to develop a model for a particular purpose. Do we develop a small model, which is very specialized for that purpose, or do we develop a general purpose model and take into account the fact that its large size and its many parameters will allow us to do better at generalizing to new problems than the small model? And that's partly a technical question, partly almost a philosophical question, which perhaps we'll have time to talk about during the rest of this multi-week period. But let's move on. So anyway, models are getting bigger. So there's models with now trillions of parameters. we won't go into the details of what they are, but there are many models with tens of billions, some with trillions of parameters. So I'd like to spend a few minutes now on another topic, which is this fascinating report, which I encourage you to have a look at, situational-awareness.ai. It's a young German fellow living in the US wrote this report where he basically, it's in a sense, it's building on the previous work that's been done on scaling laws, but attempts to explain in yet more general terms what it is that is enabling the performance of foundation models to improve continuously over time. And he divides things into three different factors, which seems reasonable to me, I would say. First of all, more computing. Back in the day, people ran neural network models on CPUs on their workstations. Then they started using GPUs. Now people are training these models on collections of tens of thousands of GPUs. So both through better computing and bigger computing, the amount of computing applied to training models has increased by, well, he estimates 3.5 to 4 orders of magnitude. So that's up to 10 to the fourth, 10,000 times relative to what it was just in 2019. So in 4 years, increased by 4 orders of magnitude. Then he points out something that we won't have much time to talk about, but people have continued to make improvements in how the training process is performed in a way that has improved its efficiency. So you can perform the same training with 1 to 2 fewer orders of magnitude compute than just 4 years ago. And then the most interesting aspect perhaps is this what he calls unhobbling, and I'll say more about that in a minute. But moving, for example, from a model that just predicts the next token to one that you can chat with makes for greater effectiveness. And so he estimates that as being another 2 orders of magnitude. So if you add those together, you get a pretty remarkable improvement in capability over just 4 years, and which is, he argues this is why we're getting results such as I showed at the beginning with this increase in model performance on so many benchmarks. Okay. So let's say a few words.
Yeah. Ian, quick question. So I mean, I'd also seen that report. I didn't read it seriously, but now you've pointed it out, so I will read it seriously because I didn't know what to make of it. But where does things like RLHF and informed fine-tuning, data curation, is that accounted for in these OOMs here?
Yeah, so I would say that would probably come under unhobbling, I think.
Okay.
Of course, we don't have A/B testing for every change that's made, but at least there's some one can count for.
Yeah. So I'm just thinking, maybe this is a pipe dream, but I'm thinking, what if thousands of universities can have as a course credit, right, helping some of those processes, right? So we could have, and it's not just cheap labor that I'm pointing to, but really, if a lot of the curation and tuning and feedback is informed, I think the potential there is quite immense. And maybe every university has its own model, right, that is tuned or it's given more data. Or anyway, just a thought.
Well, so I think there are several interesting issues there. So during this 4-year period, or roughly. So of course, the amount of computing applied has increased tremendously to the extent that you have to be a multi-billion-dollar corporation or a national lab to perform the training of the model. So that's for a university, that's somewhat disconcerting. At the same time, arguably these corporations have trained on a lot of the publicly available general purpose data that is out there. So they are reaching a wall in terms of the amount of data that is available for them to use. So data perhaps starts to become more precious. And I would also say, most of the data that's been trained on so far has been general purpose data, the contents of the web, I guess some number of scientific articles, but not too many, various public domain and non-public domain text sources. So if we start thinking about foundation models for science, then the vital question will be what data are we going to use for this purpose? And that's where universities could become very important players, is providing the training data for a next generation of science-aware models. So if you could even go, this is going a bit far, but the next challenge arguably is going to be to teach these models all that we know about science and engineering. And universities, that's what they exist to do, is to teach people about science and engineering. So, and other things, excuse me, but many of you, I think, are scientists and engineers. So maybe that's an interesting way of thinking about things. And of course, teaching it's partly assembling the knowledge that needs to be learned. It's coming up with teaching mechanisms. It's coming up with evaluation measures so you can determine whether or not someone has understood something, and then refining your methods based on that understanding. Okay,
promotion packet can just be this, Ian, right?
What? Say that again.
Your tenure and promotion packet will just be that, right? Did you assess it to improve it from where it started in that domain?
So I do want to mention, we won't spend too much time about compute, but just say, this is his estimate of the amount of time spent training. This amount of compute time, that he argues has gone up by a factor of 7 since effective compute. This is that's right. So all of these added together adds up to 7 orders of magnitude. Now, people will argue whether, is GPT-4 is really as smart as a high schooler? What does that even mean? But, by some measures, it's able to do as well as a smart high schooler in terms of evaluation tests. I wouldn't take that too seriously, but anyway, there's the 7 orders of magnitude. Point out that the world's fastest computer, as measured by the top 500 list, has gone up by 1 order of magnitude in that same 5-year period, in this case. So it's not just computers getting faster, it's many other things. And one of them is people just spending huge amounts of money on computers, to the extent now that some in the national labs even debate whether can the national labs keep up with the likes of Meta and Google and such like. Basically, over the last since 2010, the amount of, this is a rough fit to the amount of compute used by different models, about 0.6 orders of magnitude per year, whilst Moore's law over that would be 0.15 orders of magnitude per year. So that's basically mostly people spending more money, some improvements in performance of particular computers, for example, by the creation of GPUs. Okay. One impact of that is, and that's perhaps a motivation for this program we're involved in here, is that the AI advances. So there's a report by Epoch AI, and they claim to identify significant machine learning systems and then assign each an origin. And they show, and I think this would be consistent with what most of us see, is that industry now dominates. And that's, not arguably not a good thing. Okay. So interestingly, then the report goes on to say, well, what's going to happen next? And this is, what we collectively should be preparing for. So over the next 5 years, how much more improvement are we going to get? So he claims physical compute scaling will tail off a bit. Algorithmic progress, we assume, will continue to improve. And then maybe the big opportunities are in this areas of further unhobbling. For example, via the use of agentic methods, where instead of simply asking a large language model a question or a foundation model a question, you have different agents, each of which are implemented as foundation models, each of which may be specialized for different purposes. So just to give you an example of a modern foundation model then, so this is Llama 3. Some of you, I'm sure, have used that. 70 billion parameters, so not the largest, but a decent size, trained on 15 trillion tokens, 6 million GPU hours, about 10 to the 25th floating point operations. Where's that on this? Yeah, it's about up here. You can see some are greater, but it's it's within an order of magnitude or two of the biggest. And this is the paper that describes it with 327 authors. So just it's interesting to compare the scale of effort that's going underway in industry. So here's a very, I don't know if someone going to give a talk about this. It's nice work, I think. A group trained a foundation model basically on data from the materials project, which is a lot of computed data on various molecules, particularly inorganic crystals, and then being used, the resulting model being used for molecular dynamics simulations. So it's got quite a few authors in there as well. So 57 authors. The model is 2.8 million parameters, 1.5 million configurations, 2,000 GPU hours. So you can see the size relative to Llama 3 is really quite tiny. So I'd say the community is not it's not clear as to, is the future going to be a small number of very large models or many set of smaller models? My view personally would be that it's probably going to be both. We'll have very large models that will implement in an assistant manner various problem-solving strategies, calling upon more specialized models as needed. And we'll hear about some of those specialized models later today. For example, GenSlim for genetic configuration evolution. But the very large models are really crucial, and therefore we then face the question, how might we train these large models more about science and engineering? And we'll come back to that in a minute. Okay. One of the reasons why Argonne is involved in this particular training process is we have a very large computer, so we can get access to 10 to the 25th or more floating point operations, thanks to the Aurora supercomputer, which is just being unveiled at the moment. So I'll just say a few words about it. Primarily 64,000 GPUs manufactured by Intel. So an unconventional GPU, but one that seems to be performing quite well. It can perform 10 to the 18th double precision floating point operations per second. And actually more than 10 to the 19th mixed precision floating point operations. So in 12 days, it could generate, it can perform our 10 to the 25th floating point operations if that's what we want to train a model. Okay, so let's now say just a few words about this unhobbling part. I'm not, the other speakers will say more about it, but here's a little motivating narrative by Andrei Karpathy. If you see that link on the bottom left, I encourage you to have a look at it. It's a nice talk about how GPT works and how it can be improved. So he imagines here, just take a minute with me here. He's writing something down, and he wants to compare the population of California and Alaska. And he sort of thinks through the steps that he might follow. And we won't go into the detail, but the point is a human solving these sorts of problems will look up some databases, for example, Wikipedia, and use a tool, for example, a calculator. We'll do some testing, sort of what's the word, sanity checking on the results in order to generate his text. While if you simply asked a large language model to say, tell me the ratio between the population of California and Texas, it will simply predict the next token after the other, and it may or may not come up with the right answer. And I won't go into the reasons why here, but these reasons why that may not work. So a lot of so-called unhobbling work is based on using this in-context learning methods, prompt engineering, as some people might call it, to encourage models to engage in some amount of internal dialogue or monologue. Sorry, not dialogue. And with sometimes remarkable performance improvements. So I won't go into detail, but some of the things that people are doing is building in long-term memory into large language models or foundation models, so they can refer to the results of previous queries, giving them access to tools so that instead of trying to use next token prediction to work out how to multiply numbers, they instead call a calculator. Engaging in iterative activities where you keep improving on a result, providing them with context that they can consult when looking at results. And these all make a significant difference to performance. In terms of accessing tools, I thought I'd just throw up one example here, because there will be a talk by one of the authors of this work a little bit later, whose name Schwaller, I think his name is. Very nice work.
Yep.
Where they basically built a system in which a large language model is first of all extended with access to various often quite simple tools but useful tools, and then encouraged to engage in chain of thought reasoning loops in order to apply those tools one at a time. And then it's then asked to solve problems like come up with a synthesis recipe for the DEET insect repellent, which it's able to do to the level of actually generating instructions for particular robotic equipment. So if you just asked ChatGPT to do that, it wouldn't be able to, but with these extensions, its capabilities are greatly improved. So I look forward to hearing more about that later. Okay, so now let's go on and say a few words about foundation models for science. So apart from that last example, nothing I've said so far has been specific to science. And foundation models, even as I'm sure many of you already know, they can be very useful just in their current form. You can use them to summarize and distill knowledge based on whatever training data they've already been provided with, or by providing the contents of the paper to them in queries. You can sometimes you can use them to varying degrees to synthesize new knowledge. You might say, here's 2 papers, tell me what they have in common, or perhaps what results might be suggested by combining the methods from one and the methods of another. You can use them to write programs, as I'm sure many have tried, and with often remarkable success. And then people are starting to use them to generate not just programs, but plans. For example, plans for, given a set of self-driving lab apparatus, come up with, propose ways of testing particular hypotheses. And these are all, well, hundreds of people are exploring what can be done and what can't be done. And I guess we're learning some things, although it's often not very principled things. It's just somewhat ad hoc knowledge, but it's encouraging nonetheless. But we'd like, of course, to do much more than just what I've just listed. So the US Department of Energy ran a series of workshops over, well, this was 2022, so 2 years ago now. And one of the things that came out of that was a set of grand challenges in science. So these are things that people, to first order, don't know how to do, at least not cost effectively. So they're not just problems that we'd like to do a bit faster, or they're really things that we don't know how to do effectively, and therefore would believe AI methods are needed, or at least would like AI methods to help us solve. And some of these you might say, well, porting scientific codes, well, that's pretty boring and straightforward. But the point is here, the DOE complex has hundreds of millions of lines of codes, and there's no feasible way to port them all to new accelerators by purely human effort. So we need new ways of handling things, or accelerating, coming up with better representations of, say, cloud processes or radiation processes and climate models. Again, it seems to be beyond what's possible with human effort. We think that with we've got enough data that perhaps we can come up with better process representations, but it's certainly very challenging and perhaps beyond what humans can manage. So we could go through each of these, but they're all, in each case, we've got big challenges, and we think AI methods can help. The part of this, another outcome of these workshops was a set of 6 principal AI roles in science. I won't go through them all, I think, but just to point out a couple of them. So AI-based surrogates. So this is a fascinating area in which one takes, historically, high-performance computing has been used to simulate complex systems like climate or airflow, maybe the performance of catalysts by creating very detailed representations of each individual step, and often in a time-resolved system. Surrogates take the outputs of those simulations and come up with very fast AI-based approximations, which can, in some sense, be arbitrarily accurate, and therefore can allow you to simulate weather, millions of times faster, let's say, than with current methods. And I think there's a talk this afternoon about one such effort. But perhaps the most interesting thing here in this whole thing is this bottom right, the foundation AI for scientific knowledge. To what extent? Well, the reports argue that the key to progress is building out foundation AI that can automate each of the other of these elements. So whether we can do that or not remains to be seen, but that's the challenge. But how might we proceed? That's a key question. So these are some of the things that were proposed in these workshops. So some of these are actually, arguably, these are all fairly mundane, apart from the fact that doing them is very difficult. So we don't know exactly what ChatGPT and other similar models are trained on, but we can be fairly sure that there's lots of science-specific text that they haven't been trained on. So that's an area that we could be collectively doing much better at. Note here the reference to not just scientific articles, which of course are carefully curated descriptions of successful experiments. We'd also like to get descriptions of failed experiments. Much more challenging question is, how can we train on other scientific data? So I mentioned a model just now that was trained on data from the materials project, but we've got petabytes of other scientific data. Which of those data are useful for training models, which are not? Can we teach models how to engage in scientific reasoning? Can we teach them to use computational tools? So I just mentioned one project, that's the ChemCro project, that's done that for a limited set of chemistry tools. What else can we do there? And then we at Argonne and others are very engaged in coupling these models with scientific instruments. So we're pushing on in this direction at Argonne with a project called Aurora GPT. Aurora is our computer, of course. GPT is a generative pre-trained transformer, which is the architecture we're using. We're starting with an architecture similar to that of Llama, training on as much scientific texts as we can get access to, and increasingly also science data in various structured forms, and then building increasingly large versions of this model. And I'll say a bit about how we're doing that in a second. But the goal is to, well, two things. One is develop a completely open, in the sense of we understand everything that went into training it, scientific assistant, exploring the benefits of adding science data and science papers. So understanding, doing A/B testing of that sort. And then over time, probably starting later this year, starting to add in multimodal components. So particularly those that are specialized towards science, things like images, tables, equations, proofs, etc. And because despite having a very fast computer, we at Argonne are otherwise lacking in many other things. We only have so many people, we only have so much data. We've established in international collaboration the Trillion Parameter Consortium to collaborate on the construction of models like this. So we're partnering closely with people in Europe, at the Barcelona Supercomputer Center, in Japan at the Riken Supercomputer Center, and with a number of others. So the University of Michigan is an early participant in the Trillion Parameter Consortium, and there are others that are joining as we speak. So that's an obvious area for collaboration. But this is the basic idea. Train on as much text, code, and data sets, build a foundation model that can then be specialized to a variety of different tasks. It could be specialized via fine-tuning or by in-context learning or some other emerging method. But we're pushing hard on this notion that a general purpose, very large open science foundation model is at least one important part of the future of AI for science. I could ask if there are questions at this point, by the way. I know I said I would earlier and I didn't.
First, we go around in the room. Are there any questions, comments on his content so far?
I have a general question
Yeah.
about the training phase of these foundation models.
Yep.
So I was wondering, is there a way to to tell the model what to learn and what not to? Because if we give it access to a lot of information on internet, let's say, there are a lot of misinformation on them. So it seems to be quite dangerous for it to learn something that is wrong. So is there a way to kind of guide it to just learn correct information?
Yeah, so there are, that's of course a critical question that people are talking about a lot. So, I mean, one way one can do that is by careful curation of the data that is used for training. And you know, that's certainly something that groups that we work with, like the Allen Institute for AI, is engaged in that we are engaged in with our collections of scientific papers that we're creating. That, you know, particular groups might want to engage in, and, you know, creating carefully curated collections of material for training. And I would say that, you know, awareness of the importance of quality over quantity is growing as people experiment more. So, you know, there are probably hundreds of trillions of tokens of web data. You know, this is web crawl data, and web crawl data does seem to be important as a means of providing general information to models, you know, that you wouldn't find in scientific articles. But of course, as you say, it has a degree of the quality can vary quite a bit. So curation is vital. And then the question is, how do you evaluate the quality of data? That's that's a topic of great concern at the moment. Another a question I've been asked in the past is also, you know, we're training on archive, as a, you know, the OpenAI corpus includes archive papers, but archive papers have not been peer reviewed. Some of them are probably nonsense. So how do you deal with that situation? So I'm not sure of the answer there.
Yeah. I mean,
another thing. Yeah.
So
go ahead.
Just to add, so you spoke mainly about the pre-training, right? But during the fine-tuning stage, with reasoning in a supervised way, we can teach the model also what is not right and for what reasons, right? So I think that's where this large manpower can also be very useful.
Yes, no, I agree. Yep. I mean, I was going to mention another thing which is, you know, knowledge, human knowledge evolves over time. So you might use training regimes that emphasize more recent publications. But yes, you would like to think that your model could, instead of proposing answers without thought, it could reflect on those answers and see whether it's contradicted by anything that it's seen in previous, in its training. So
there's one more question in the room.
Yeah, please.
It's a bit on that topic, but you know, like Copernicus thought that, you know, the Earth was not the center of the universe, right? The sun was.
Yep.
But prior to that, sun was the center. That was the truth. So, like, how do you handle those types of like situations where, you know, the prevailing knowledge is potentially wrong? Like, how do we train these models to like learn what is true?
Yes, well, assuming we don't want to get into the philosophical question of what is truth, but my colleague a colleague of mine at the University of Chicago, James Evans, he argues that strongly for temporal training, where you train on more recent publications before, you know, first of all, you may train on early things, but you keep training on more recent publications over time, so that the more recent publication results dominate the model, what the model learns. And that, you know, it seems to be, I can imagine that would be quite useful and important to emphasize at least the more recently developed knowledge. But there will nevertheless be things that the model knows that are wrong. There are certainly things that the model will be asked that it doesn't know. Otherwise, the whole purpose of having these models would not, at least one of the purposes, which is to help with development of new knowledge, will not be useful. Yeah, so perhaps it's what was just mentioned, I think, by Karthik about, perhaps encouraging the training the models to engage in reflection and come up with ways of testing the hypotheses that they come up with.
Ian,
But ultimately, these are limited. If I think it's easy to, assume superhuman capabilities for these models. If they are, if they were absolutely perfect, what they would be equivalent to someone who had read all of the scientific literature and was able to recall and identify connections across it. And if you were that person, you would, of course, know some number of incorrect some number of inconsistent things in what you would want to do, hopefully. And that's maybe what a lot of research is about, is be able to identify the inconsistent things and help from that learn, identify things that are perhaps incorrect.
Yeah, Ian, when you conceived the Aurora GPT work, at that time, what did you estimate was the compute gap that you would be able to bridge? Like, you sort of showed this, estimate of MACE, being 0.01% or lower compute wise. Where do you think Aurora GPT will land relative to whatever would be state of the art by that point?
Yeah, so I've got that. We've got estimates of that, and I don't remember them. But I think with the, if we could get access to all of Aurora, we'd be competitive with at least competitive with, perhaps ahead of the very best or largest commercial systems. Of course, Aurora is a national resource, so we can't get access to all of it. So we're still training on smaller fractions while we submit proposals for the time that we'll require to perform the larger runs. But we'll be operating at a similar scale, I think, to the very biggest ones of today. And the size of the orders that we hear about people placing for GPUs suggests that maybe we won't be competitive in 2 years' time, say.
Yeah, I think this is one of the key reasons for sort of the need for. I'm so glad you guys have set up TPC and the sort of vision here, right? To be able to give access to this scale of open foundation models, especially around being able to have a reliable collection of all the training data that went into it and the training procedure and so on, which obviously, as you said, right, even with the Llama 3 and others, right, the model is open. That doesn't mean that all the procedures that went into what was done is clear. So it's commendable what is being done here.
I mentioned also there's a lot of activity going on in terms of federal government planning and discussions relating to much larger resources for open and scientific AI, the FAST initiative, Frontiers of AI for Accelerating Science and Technology, which is still, it's been discussed, but it's, there's people bringing forward potential legislation to fund that program at quite a large level. So we're probably running out of time here, actually. So I'll just say a few words about what we're doing in terms of organizing ourselves to create Aurora GPT, and the the 5 key elements here, which I'll just preparing data, training, that's pre-training, Post-training is the the fine-tuning, reinforcement learning, etc. Evaluation, where we determine how good the model is for particular purposes, and then 6, serving is where you allow people to access the model. And of course, we're gonna have users who want to perform millions of queries against the model once trained. For example, people working on drug design want to be able to try millions of drug candidates and see what the model knows about them. So high performance serving is important. But in terms of science, I just wanted to emphasize here 2 things. So training, we know how to do. We need big computers to do it, but it's sort of there's nothing special, at least for now, about training a model for science versus any other model. It's arguably similarly for post-training, although there may be post-training we want to do to specialize for scientific inference, etc. But I'd say the two areas where really very specialized work needs to be done, and where we would like to be partnering with Michigan and others, is preparation of scientific data to create a model that's specialized for science, and then evaluation tests that allow us to determine whether the model that we've specialized for science is actually any better. It's with the current, there are lots and lots of tests out there, but most of them are intended to see whether the model is biased or whether it can do simple arithmetic or, do this or that. It's not particularly, they're not particularly focused on whether or not a model can help someone engage in discovering a new material, for example. So data preparation and evaluation are the areas where big changes are needed. So these are some of the people involved. You'll know some of these guys and gals. This is to point out that this is the data used to train one of the mid-range models, Palm 540B. Just point out science is a pretty small part of it. Bigger than adult content, but smaller than sports. So obviously we'd like to, we think expanding that will make a big difference. So our initial goal was to assemble 20 trillion tokens. So we've got all sorts of scientific article collections. We've got ACM has provided us with their material. We've got arXiv, bioRxiv, chemarXiv, some other data sets that are less open. If you have ideas of text data sets that you'd like to provide, then please let us know. We're putting a fair bit of work into deduplication of these things. So you don't want the same content more than once, because that will bias in terms of if it sees some things many times and some things a few times, then that's not, it will learn the first thing more than the second. So lots of data. I think a key question now is, and the people here may have thoughts, how do we go beyond articles to data? So there are some nice domain-specific databases like PubChem, UniProt. So we can think about how to turn those into data that the model will be trained on. And there are other much larger data sets that perhaps are lower information content, but still valuable. So we're trying to work out what to do with those. So here's an example of how at least one group involved in the project is processing genomic information. So there's a large database called SEED, describes information about genomes found in various bacterial species. And so the step that's been taken here is to automatically generate textual paragraphs that describe what's in the database. Now, is that the right approach? I'm not sure myself, but it seems to have some promising results so far. But this, you'll get here. The genome with identify blah has this many base pairs and this name. It's considered a reference genome. it might say, it has so many protein coding regions, it encodes for this, it's known to encode for this protein, etc. And then we'll feed that in as basically this scientific article and train the model with that data. Alternatively, we could train the model to know how to read the seed database. We're not sure which is better. My colleague Rick Stevens, some of you know well, likes to try and get people thinking big. So we're right now trying to work out how we can get 20 trillion tokens to train Aurora GPT. How are we going to get let's say we wanted 1,000 trillion tokens, then encode all scientific knowledge. What would those tokens look like? Where would we get them from? Do we need to perform new experiments or simulations? Are there databases we can be mining to get those tokens, etc.? So I hope we can spend some time during this session talking about those things. These are all made up numbers, by the way, just to be. And so, there are lots of interesting questions we can be asking about data, which I won't.
Ian, those numbers are made up, but the ratios, was there some thought given to it?
I'm sure there was, but I haven't actually asked Rick that question.
Very small computer science.
Yeah.
Yeah. So what is computer science knowledge? Is it the contents of software, proofs? You don't tend to perform exhaustive measurement campaigns on systems. But so accelerators is very large because there are systems like the Large Hadron Collider and other things that collect huge amounts of data, petabytes and petabytes. Now the information content of that data is arguably quite low if you look at, say, the Large Hadron Collider versus biology, where perhaps the tokens are quite processed. They represent the interpretation of many large numbers of experiments.
Yeah, I think generally when in fields where there's a discrete finite alphabet, like materials and biology, I feel this would be very successful in many things. I mean, it's easy to, I wouldn't say easy, it's certainly feasible to generate 1,000 trillion tokens of numerical simulation data, right, from PDE solvers. But yeah, that's not a finite alphabet, so yeah, it may not be very useful.
Yeah, and what is the information contained in there?
Exactly.
Maybe it's just the equations that went into the simulations.
Correct.
Interesting. Yeah. Anyway, so that's something to think about, I think. And then I'll just say a few words perhaps about, so this is a bit about the pre-training process, which is, we've adapted well-known software to run well on Aurora. It's running well. Just to mention an odd, the well-known phenomenon in these training processes is the models will periodically explode. No one is quite sure why. It may be a software glitch, but usually one then just restarts from a checkpoint and things go well. I won't say more about that. Evaluation. So the evaluation I've already mentioned is a very important area because, what the whole purpose of creating a science-specific model is to demonstrate, is to create something that's better at scientific purposes. But how do we determine whether it's actually better? Of course, we can give it to people and they can use it. That will be, but that's a very informal process. Having better evaluation tests will be important. So my colleague Frank Capello and a team at Argonne is creating collections of multiple choice questions, MCQs. So if it will be a wonderful thing of people participating in this course, we're able to spend a little bit of time creating these multiple choice questions. The idea is you take a paper, and then you create, I don't know if we've got a, oh, I haven't got one. You go to this, take a picture of this. Basically, you take a paper, you come up with a question, a true answer, and a set of confounders, incorrect answers. So in a sense, it requires a fair bit of thought, but it's not a lot of actual typing. It would be great to get people helping with that. We have about 100 so far, and there's actually a tutorial going on today that we hope will generate another 100. But if you could generate 100 from this series, this workshop, that would be wonderful. Any other questions at this point?
Anything
Comments?
online? It's been very quiet.
Inference?
Keep going for now.
Yeah.
No, there is a question here.
Elaborate a bit on the spikes you mentioned during pre-training, and you also mentioned that you can avoid them by restarting from a checkpoint. So how exactly?
So how is that done?
Yes, please.
Well, basically, we checkpoint the model, the state of the model periodically, I think several times per hour. I don't remember exactly how many. And then we can stop the computation, then restart it and get it to read in the state of the checkpoint, and then continue execution. And sometimes I think it's also bad data generates results in these explosions, and so you skip the data that it was training on at the time of the failure.
Is that done like automatically, or does that require like human intervention?
I think it's automatic at this point. Yeah. And this is, other people training large models have recounted doing the same thing. Yeah, if you're running fast enough, then it becomes frequent enough that you want to do it automatically. So there's a fair bit of this sort of, what's the word, folk knowledge about how to make pre-training run well. There we go. See, down the bottom, automatically detect spikes and identify the checkpoints to restart from to avoid the spike. And there's some work that I think is now completed on so-called zero overhead, basically parallel checkpointing that will run in parallel with continued training. And then there's interesting, if you're a parallel computing person, working out how to distribute the training process across different parts of the training process across different nodes of the Aurora system. Okay, so here, as I was just saying, what opportunities for collaboration. So the word pipeline appears many times. Basically, that means getting the software required to do different things up and running efficiently. And certainly there's opportunities to help with aspects of that, but that's mostly under control, I would say. But certainly in terms of understanding the goals for the overall Aurora GPT, assembling and cleaning, evaluating data, building out evaluation suites, and then applying the model to science problems. These are all areas of great interest. On the inference side, this is the goal here, is to allow people to run many queries and being able to do so very efficiently. So there are interesting computer systems issues there, for both model design issues and computer system issues. On the model design, you may want to reduce the complexity of the model, by quantizing or removing, that's reducing the amount of resolution applied to the model weights, or eliminating some weights automatically if they don't have a big impact on the output. And then in terms of scaling, being able to run many models at once on a single GPU is another interesting challenge. Okay, so I thought I've got a few slides here which I developed with Arvind Ramanathan, who is going to be talking later, but I thought it might just give some interesting ideas about how we want to be using these models going forward. So this is an application that a team at Argonne has been working on for some time. The goal, it's not a materials design problem, it's a chemistry design problem, I guess. But the idea is to come up with identify antimicrobial peptides, small sequences of amino acids, 12 to 50, as we say here, that have the property of being able to destroy various forms of microbes without damaging a host cell. So obviously, it's a very complex problem. There's a huge variety of potential antimicrobial peptides, and there are many different ways in which one of these little things can interact with a host cell in particular. But so it's an interesting scientific problem and an engineering problem as well. And very knowledge intensive. So, you want to know about all sorts of things. How do bacterial cells operate? How do antimicrobial peptides operate? How do host cells and their intracellular pathways within the cell operate? These are all things that we would like to be able to explore in some principled manner, and we might, as said here, use a mix of searching the existing knowledge, performing simulations, performing experiments. So Priyanka Sethi, a student of ours, got started on this by building out a simple, what you might call an agent using ChatGPT. This agent is designed to ask, which organism is this particular supplied peptide acting? So it's a very simple question. And it's implemented via this technique that you'll hear more about later in this workshop called retrieval augmented generation. The idea is that you're trying to ask a foundation model a question, and rather than saying just answer this question based on your parameters, you're saying, here's some documents that I think are relevant to the question. So based on these documents, what answer would you give to that question? And in this case, we might retrieve these documents from PubMed simply by saying, find abstracts from PubMed that reference the peptide in question. So it's a very simple form of agent, but you could, I think, see how that could be then linked into more complex workflows, maybe one that's going to run through and test a whole series of peptides or generate new peptides based on feedback from previous ones. A couple of things we want here is, one is we want a model that knows a lot about peptides and related topics. So that perhaps suggests a need for a model like Aurora GPT that's trained on more than just whatever ChatGPT is trained on. And we also want to be able to make millions of requests because we have millions of peptides we want to evaluate. And so we want to be able to do inference at very high rates, faster than we could with ChatGPT. So a couple of reasons here for wanting to build Aurora GPT motivated by this. And Priyanka and other students have been building a whole set of such agents. So this is up at the left here is the one I just talked about. Others will run simple computations to predict protein structures. Another will use other methods to evaluate structures. And we can link these together into a flow. And now we've got something that can go through and, given a set of input peptides, can extract some knowledge, determine a structure, and evaluate the structure. And if we wanted to maybe use HPC for running things, then we have an HPC agent that knows about how to run things on HPC. We also might, at some point, and we're starting to do this now, we'll run experiments to test the effectiveness of antimicrobial peptides that survive that pass through this pipeline. And based on that output, well, these are some of the self-driving labs we have at Argonne that are set up to be operated by this overall system. Each of these is implemented using common interfaces that we've been developing over the last couple of years, so that they can be controlled by foundation models as needed. And then we can then feed back into to generate additional peptides. So a pretty simple pipeline, but this is the sort of thing we want our foundation models to be able to do. And hopefully you'll have time during this workshop to think about how to build, what sort of agents would you like to build for your particular applications, and how might you then link them together to do interesting things. Okay. And I'll just maybe say a few words here about this notion of agent. So it's actually a very an old term from computer science. So an agent, at least one definition, is a computational system, persistent and stateful. So state is important. It's long running. It can accumulate information. It can interact with its environment. That could be by performing an experiment or running a simulation. It can sense its environment. It can determine the result of an experiment or a simulation. And then it can adapt its responses over time to learn from those interactions. So I myself see the future of AI for science as being about building embodied agents of this sort. And that's perhaps where we get the next dehobbling step for our foundation models. Okay. And we need
Ian,
many of these things. Yeah, go ahead.
Yeah, I think Jan has a question. Jan, can you unmute and ask?
Yeah, please unmute and ask.
Sure. Yes. So in particular, what you just showed, right? So like, what part should the agent do, and what part does the model do based on its general knowledge, right? So do you have a feeling where there would be distinction? Like, what task is where the general model is good to answer it, and what would you specialize and put into an agent?
Yes, that's right. So there's an attempt to capture that here, although I'm not sure that it's this is a figure I just found, and so I don't know if it quite captures it. But so a user says, find me an antimicrobial peptide that is able to act against the COVID virus, say, in SARS-CoV-2 virus. But that's, so then you need the agent is then perhaps able to interact with your foundation model by making a series of, you might say, well, come up with a hypothesis or a set of hypotheses for ways for suitable antimicrobial peptides. And then you might do another query, say, we'll rank these based on the following criteria. And then, how would you, then you might ask it to test the hypothesis, and it might say, well, I need to run AlphaFold to determine the structure of each of these antimicrobial peptides, and then see to whether those structures are such that they can interfere with the docking of the COVID virus, or something like that. So there's a series of interactions of that sort that occur, and I think so some of this is created by prompts that you generate to the foundation model. Some of the prompts perhaps are themselves generated by asking the foundation model to create the prompts. You can operate at varying degrees of abstraction, I think, and my impression is people are still working out how best to do those things.
Okay, thank you.
What do others think about that? Any thoughts?
I think it's learning and doing and iteration. There is no straightforward question. But, I mean, this issue comes up in any inference task, right? So it's almost like the bigger model is your prior, right? And then you have some amount of information or action, and you got to balance the two. If you have a perfect prior, then yeah, it's probably not an issue. But yeah, I don't think this question will ever be answered. Is my answer. It's just like
we want to. So it was mentioned. I think perhaps I can't remember whether it was Venkat or mentioned this at the beginning. What does AI for science mean? So is it creating an entirely autonomous discovery agent, or using AI to accelerate steps that are fairly mundane, to be the intelligent assistant?
Yeah, and I'm very much in the second part, right? Where I actually believe even if we are not going to get the orders of magnitude improvement like the ones you showed in your various slides, if the user is sophisticated and we build good APIs, you can still be incredibly useful, right? So so
humans are very smart. Yes.
Yeah, and we can use this to just do things that we don't want to, or it does not involve complex reasoning. That's the base use case, but there are other opportunities as well.
And we're all we're effectively using computers that are 10 to the 15th times faster than those available 100 years ago.
But
we still are limited.
And the point you mentioned earlier, right? So even if these things are not truly intelligent, even if they're not emerging, well, this is not what you said, but at least my thought on what you said. Even if they're not emergent, even if they're not intelligent, the fact that they've read all the papers that exist and they can recall and connect, that by itself can be incredibly useful with a sophisticated user.
Yeah, exactly. Yes. Yeah. So capabilities are emerging now. Those capabilities, it seems, people argue as to whether that's general intelligence, artificial general intelligence, which seems a bit silly to me, but but it's sort of beside the point. Whether the thing is they're useful. They're either useful or not useful for us.
Yeah.
Okay. So that was a final slide. Yeah.
Great. Yeah. Thank you very much. This was fantastic.
So what are you gonna? So will you have a final? People will present at the end the remarkable developments that they have made during the 3 weeks. That will be fun to listen to.
Yes. Yeah. Each of the hackathon teams will present at the end on what they have accomplished.
Yeah. Great.
I think we have amazing human brain power in addition to compute power. So we'll see what they all achieve.
Yes, if you haven't looked at my colleague Ben Blazek, as was mentioned, ran along with several others these 24-hour large language model hackathons, which produced some really fascinating outputs. It's worth having a look to see what they did.
Yeah, we were very impressed. In fact, we were inspired by some of that in designing our program. So
good.
Yeah, in fact, I think Jan led one of the hackathon there.
And that's how we found Jan, actually.
Yeah, for the Langston
very
work.
Good. It's truly a global community. That's great.
Right.
Hey, well, thanks everyone for your attention today. I appreciate it, and it's good to see you all there.
Thank you very much. And yeah, we'll have multiple touch bases, right, during the next 3 weeks, especially tomorrow afternoon. We would really like to have your presence if possible. Yeah.
Yeah, I think I'll be there, but let me check.
Okay.
We've got a Los Alamos visit. That's about the only thing going on this week, I think.
Okay. All right.
Yeah.
All right.
All right.
Thank you very much.
Thanks, guys. Have a good afternoon. Bye-bye.